All right, now it is recording. Welcome to the session, everyone. Thank you, Aditi.
Thanks. So I'll be giving a demo on NT FITs, that is N-channel tunnel FITs. So tunnel FITs are basically based on a type of conduction which is uh, tunnel. So it's band-to-band tunneling. It's based on band-to-band tunneling rather than thermal current, like in your normal MOSFETs. So whoever is more interested can approach the answer. Okay, so
So in this presentation, Aditi will only show you a demonstration on how to use synopsys tools, TCAD tools, to simulate the tunnel fits. What are its characteristics? That's it. Okay. So now it is the end semester, so we are not going to kind of give you lot of kind of work based on this. So after your end semester is over, as part of your research practice and also for your placements, whatever, we will essentially give you jobs or the tasks to do on this. Okay, so as of now we are going to learn only how to use the tool, TCAD tool. Okay. Yeah.
okay. So I gather it's the first time that you all are using this tool. So basically this tool has various components. The first one is going to be Centaurus Device Editor, SDE. And for opening that, first of all, we need to create a folder from which we will launch this particular tool. So let's name this folder according to what we are doing today. From here, from inside this folder now, we can, first of all, right click. Then this pop-up will appear. From here, you can select open in terminal. And from here, you can type STE space ampersand. So this opens this device editor SDE for you. So there is a blue screen and then there is the scheme commands. Okay, today's there is some problem with the scheme commands. It depends on the server actually. I don't think scheme commands will show today. They are coming as boxes, but usually what happens is that whatever you draw here, so this blue screen is for drawing your structure. All these icons are used in drawing your structure. You can select different materials. This is the materials list. Then these are the various shapes that you can draw. Like nowadays there are nanowires and also there is circular shape and all that. You can draw either 2D or 3D structures. So as what we'll be drawing today is 2D mode. First of all, go to this view. From here, from the drop down menu, you can select GUI mode. And from here, take on 2D mode. Okay, next thing that you have to do is go to this draw icon, deselect auto region naming, because if you keep it selected, then it will give its own random names. And if you give your own name, then it will make things simpler in the future. Okay, as you can see, there are some boxes coming here. Usually there are commands in simple English language. So in advanced structures, what we do is we usually prefer commands rather than this drawing, because if we have to make any changes, then commands make it easier. Anyways, since it is coming in boxes, let's just close it for the time being. Just concentrate on the structure itself. So we have deselected auto region namings and we will select exact coordinates from here. Exact coordinate means now whatever you draw, it will ask you for the coordinates rather than some random selection. So now that we have made all these changes, let's start drawing. So basically we want to draw a rectangular region. So from here we can go to 2D create tools. From draw, drop down menu, 2D create tools. We can select rectangular region. Either you can select it from here or you can select it directly from the menu here, given here. Okay. So now when you draw something, so this box pops up. This is a box for exact coordinates. From here you can give exactly which coordinates you want. Now a rectangle can be defined by two opposite vertices. So that is what this indicates here. First vertex is like, let's say it's 0, 0. These are x and y are coordinate axes. Let's start from 0, 0. And the second vertex is the vertex opposite to this, which defines the rectangle. So here we can give our dimensions. Like for example, say for this particular anti-FET, we want our source region. We will be defining the source region here. So we want our source region to be, say, of the order of 30 nanometers. Now these boxes by default, they take measurement in micrometers. So for 30 nanometers, we will put this value. And for depth, let's say body depth we are taking as 10 nanometers. These are not just arbitrary values based on many experiments. These are found to be the most optimized for giving the best values of current as much as possible. So let's say OK to this. As you can see, we have taken the depth to be very small because we want it to be a fully depleted structure. Let's name this region. I'll name it as source P. You can give any name that you like. This is going to be a P-type source. Okay. One more thing, we have to select the axis here as x minus y. So x-axis, like you normally put x-axis, but y, positive y is in the opposite direction. So this is the norm which is used. Okay, now let's yeah, one more thing. This has to be in silicon germanium. I'll undo this. It'll be good for your practice also. So material that we select from here should be silicon germanium. TFETs usually operate better with silicon germanium material. So we'll select silicon germanium. Again, we'll draw the source. Okay. Given the same measurements as earlier. Okay. Okay, let's draw the channel region now. I'm taking the channel region to be 15 nanometers in length. So you can see already the first vertex is given as the end point of our first rectangle, which is source P region. We can take the y coordinate to be 0. In the opposite vertex, we'll define the length of the channel first, since I'm taking it to be 15 nanometers. Starting from 30 nanometers, it's going to be 0.45. And the depth, as we did earlier, is going to be 10 nanometers. So this is our channel region. Okay, let's draw our source region, drain region now. This drawing can be wrong also, because you can always correct it in this pop-up window. So we are starting from the last length. It ends here at 45 nanometers. Okay, this again will take as 30 nanometers. So 45 plus 30 gives us this value. And then depth, as earlier, will take as 10 nanometers. So this is the drain region. I'll name it as drain N. Okay, on your left side column, there is this shortcut which says zoom to extends just below the hand. If you click this, this will come in fit right in the middle. Okay. So now we'll put a thick peridoxide at the back side of this structure. So for this, we'll take silicon dioxide. Again, we'll start our coordinates as 0, 0. Length it's taken correctly. And let's take the depth as 20 nanometers for now. We just want it to be very thick. Naming it as Peridoxide. Okay. So then for the front gate oxide, we will take a very high K dielectric material, which is silicon nitrate from here. So already our starting point is the lower left side bottom vertex. So we'll give the coordinates for this. We'll make it through the entire length. So now the thickness of this oxide layer, we are taking it as very thin because that is what is the most optimized for a TFET operation. So we'll be taking it as 3 nanometers. So adding 3 nanometers to this 10 nanometers, which is the starting point, we get this value. Okay. I'm naming it as gate oxide. Okay. And now we'll finally make the gate metal region. We'll take aluminium for this. Again, all these materials are not arbitrarily selected. Whoever is interested can go into the depth of why we select a particular material for gate. So the gate metal has to overlap the channel over here. So it will start from,
Excuse me, Aditi, you
yes, sir.
carry on. I'll just remind the students. Uh, Students, you can see that Aditi has chosen aluminum for the gate material. Okay, so those of you, like all of you, were there in the physics and modeling of microelectronic devices. Recall that aluminum has its work function, which is very much closely matched with the electron affinity of the material. Okay, material which is used in the channel, silicon, germanium, or silicon, right? So essentially what happens is that, remember, Aditi is making one n tfet. Okay, if it is n channel, that's why we are going to choose a material or the metal for the gate terminal which is as close to that. That means the Fermi energy level is as much aligned to the Fermi energy level on the channel material as possible. So aluminum is that material, remember. And this theory is very much similar, I mean it's exactly the same as the MOSFETs which we had studied in our PMMD course. So please recall. So what I want you to do is, whenever you, this is of course a demonstration on how to use the tool. So this tool is essentially garbage in, garbage out. So remember, instead of aluminum, if Aditi has chosen, for, like she has rightly said, we have optimized this device for best performance, meaning that there is a reason for selecting silicon germanium. There is a reason for the each of the dimensions which she has used, and there is 100% physics and engineering which are involved over here. So make sure that once you have essentially done the simulations, the results should make sense. So if somebody asks you, why have you selected this oxide layer so thick, whereas this oxide layer so small? Okay, you should be ready with the answers, and that is where people will be asking you questions. All right, so be clear on what results you get, be clear on why you are using this. Otherwise, this tool will essentially give you whatever results based on whatever inputs you give. Okay, so make sure. So I am always emphasizing that this tool is just a tool, it's not the end of the story. So if you want to publish a paper, if you want to present this research work in your uh, interviews, for instance, in your placement interviews, then the interviewers are going to ask all about this. Okay, thank you, Aditi, please continue. Thank you.
Yes. Yes. So we are drawing the gate metal. So we'll start with this point over here, which is it should overlap the channel region. So we are taking the length as the end of the source region, and the depth is where this depth ends. Remember, this was the vertex 0, 0. So this is 10 nanometers, over which this is 3 nanometers. So we'll go for 1, 10 plus 3, 13 nanometers. Channel length we have taken is 15 nanometers. So starting from 30 is 45, the endpoint is 45. And we'll take the thickness again here as 3 nanometers. So starting from 1, 3, it will give you this dimension. Let's name this region as gate. Okay. So now you can see our structure is complete. So what is left, as you may have already noticed, is that we have to still dope this. This is just pure silicon germanium, and we have to still dope these regions. So for doping, what we'll do is, from this menu at the top, we'll go to device, constant profile placement. From here, we can select these regions. Here under placement type, you can go to regions. Already source P is selected. We can give a placement name which is corresponding to this. Constant profile definition name. Okay, since this is a P-type source, we will dope it with boron concentration. And we are taking the doping concentration as 10 to the power 20. Again, these values are based on much research and whatever works best for the best current value. Then next we'll dope the channel region. Channel will dope as, channel is theoretically said to be intrinsic, but as you will see that this is not completely, like it is still relatively heavily doped, but as compared to other regions in our NT-FET only source and drain region, it is relatively lightly doped, but otherwise you will not actually channel, can see will dope it with arsenic, which is group 5 impurity, N-type impurity. And you can see I'll be doping it with this value. This is not very light value also. So what I meant to say was it is relatively light as compared to the other two regions, source and drain region. This is again best, whatever was found to be best. Okay, now let's go to the drain region. You can put this window aside and you can see that as you keep on changing these regions become highlighted. The highlighted regions come in this orange color. So as you select source P, this first region is selected, then channel middle region is selected, and now we are going on to drain region, which we still have to dope. I'll just give corresponding placement name and profile definition name. We'll still stick to arsenic as an impurity for N-type impurity. And for this, we will take the value 5 to the power 18. Actually, once you are doing it, you can play around with these values to see whatever is giving best, but don't take very large difference from what we are taking here. You can make small changes and see how the current is changing. Okay, so now we have doped this correctly. Let's check it once more. So from the uppermost, we'll select source. It is selecting source region. It's boron, group 3 impurity, 10 to the power 20. Then channel, group 5 impurity, 10 to the power 17. Again, drain is P-type, 5 into 10 to the power 18. Okay. You can close this window now. Now, next thing we have to make contacts from where the voltages will be applied. So for this, we'll go to this icon over here, contacts. From the drop down menu, select contact sets. So you can give the contact names one by one. I'll just give simple names. S for source. You can select the edge color. It's in the pattern of RGB. So here it is 100 means red is 0, G for green, red is 1, G for green is 0, blue is 0. So it will be of red color. You can set it from here. Then for the drain terminal, I'll stick to the same color. I'll stick to red only. Then for the gate terminal, let's take a different color this time. Okay, so this is a green color now. Okay. So we can keep this window open here. From here we have just defined these contacts. We have not placed it on our structure yet. So for placing it, let's select the contacts one by one. I'll start with source contact. Click activate. From here, this menu, you can select, already it's on select body. We have to put it on select edge. Okay. Now wherever we click with this cursor, it will select the edge. Okay. So we have activated the source contact. So this is where we are going to place our contact. Okay. So finally this got selected. Whatever got selected, you can see it's in the highlighted color, which is the orange color here. So after this, we'll go to contacts, and we'll say set contact. Once we put it at set contact, we can see that the region has converted to red color, which is what we set as the color for source. Similarly, we'll select drain, click activate, select this region. It is highlighted now, and we'll go to contacts and say set contact. Now drain is also set. Gate region, activate, select where we want to put our contact, go to the contacts menu, and from there set contact. Now all our contacts have been set. We'll close this window. So this is the main structure of our device. Now for calculation, for the simulation purposes, we have to apply voltages and calculate currents. For that, we'll put a mesh here. Mesh means kind of a crisscross net kind of a thing. And at the crossing points, the voltages will be applied and the corresponding currents will be calculated. So we'll put the mesh structure first. Go to the mesh icon. From there, the drop down menu, the first one, define ref eval window. From here, select rectangle. So we'll select the entire device first. We'll give a name to it. Let's say, since it's the entire device, so I'll put all here for my reference. Okay. Again, go to the mesh icon. Go to refinement placement. From here, we can select this window, which we just defined, and we can give its details over here. Again, I'll give a corresponding placement name and definition name. Okay, so here for the entire device, we'll give a kind of a coarser mesh. Then for the channel itself, where the actual action is taking place, I'll give a, say, a 10 nanometer size in both directions. Since this is a 2D structure, Z direction will be 0. Minimum element size, let's say I'll give as -3. Remember that the finer we make this mesh, the more time it is going to take for the calculations. Because at each and every point of the mesh, the calculations, the Poisson's equations will be applied to calculate currents. So we have defined this mesh for the entire body, that is. We'll close this window now. We'll define another mesh, a finer mesh for the channel region. So we'll make a selection that covers the entire channel region. I'll change the name. I'm just changing the extension of it for my own reference. Again, go back to the mesh icon, go to refine placement. We'll just define this channel mesh. So we'll select it from here. And here the mesh can be finer. So let's take it as, say, 5 nanometers. Minimum element size can be slightly less. Okay. So we have defined the mesh structure for this device. This is where the action is taking place. So we are taking the finer mesh here. We'll save this model now. We'll give the file same name as the project name. Okay. And now we'll, from the mesh icon, drop down menu, we'll go to build mesh. So this is opening the Centaurus visual. Here you can see that from Centaurus visual, we are seeing the same structure that we just built. From here, we can see the different doping regions. This is the source regions. Source region. So this is, you can see it's coming as 10 to the power 20. Minus means it's a positive. It's the accepted impurity. Then this is the most heavily charged donor impurity, negative this thing. So this is, as we put it, as 5 into 10 to the power 18 of the type 5 arsenic. Then this is in the middle. Channel is slightly intrinsic as compared to the source and drain regions. Now we can select the this from this left menu, we can select this grid type of a thing. Once we select it, we can see the grid that we have applied. As you can see, I have not applied very fine grid here. So the entire structure, there is a coarser grid, but on the channel region, there is a more finer grid over here because the main action is taking place here. So we need more nodes to calculate current accurately. Okay. So now that this is done, we'll apply the simulation, we'll apply the test file to it. We'll go to our folder, NTFET demo. Okay, we need a commands, a test file for this. I already have a test file. I can, sir can share it with you also in case you want to pursue this project. Excuse me, sir.
Yeah, please tell.
Sir, actually, this different servers don't copy the files accurately. So I think I have the file on a different server. Can I just log out from this server and log in from a different server?
Like you are essentially trying to copy the CMD file, I guess, right?
Yes, sir. Yes, sir.
The CMD file should be there in the others also, no? You can open up the info.
That's what. That's what the my other structures na they are on a different server actually. On this server they are not showing. This is discrepancy I brought to the notice of Rajshekhar sir also, that if I work on one server,
Mm-hmm.
whatever I am saving, it's not showing on all the other servers.
It should not happen actually. Please show me here.
So it was
Good.
on desktop only.
Uh-huh.
So this is NTFET demo. That was the that is by the name of NTFET new. If I just log into 243, I'll show it.
Okay. Okay. Let me see once. All right, you can do that, of course. So
Okay.
what I'll suggest is no need to switch it off because you have already shown the demo in this server now. So let it
Hmm.
be. What I'm
Hmm.
suggesting is you open up another remote desktop.
Okay.
You open up another remote desktop, log into 243.
Okay.
Uh, just log into 243. You just minimize this remote desktop. Yeah, that one. Correct. Now you can log into another. Uh,
But so that's not happening because as soon as after I minimize this, as soon
hmm.
as I go to this
No, no,
icon, it is
right
showing
click,
the same.
right
Acha,
click,
okay.
new window. No, no, not close window. Yes. Okay, this is already open. So you open up another instance of remote desktop. You go to the start button. Yeah, there.
Yeah.
Perfect. 243. Yes.
So here it is showing.
Yeah.
So basically, I'll be copying this file from here.
Yes. Yes. You. How will you copy? What I'd suggest is you. This one is the file we are looking for, right?
Yes, sir. And the one that I'm showing actually is that NTFET demo. It is not showing on this
No, because you
particular.
have not logged out. Probably that is the reason why this has not been synced. Remember,
Mm-hmm.
like it is a knowledge for the students also. Unless and until you log out of a session, your session will not be synced. Okay, doesn't matter. You just see it. It will not be
It is
pasted.
not. It's not
It will
pasting
not come.
across the.
Doesn't matter. You go to the other server, or else here also it is possible.
So I can continue this with the other server. I have made the same structure.
Yeah, yeah. Then what is the
Huh?
problem? Then you
Okay.
continue from there itself.
So I'll just. This is the copy of what we have already done.
So what I'll
Only.
suggest is if the structure and everything is the same, then
Yes.
what you do is you open up with SVisual and SDE from this
Hmm.
server itself.
Yes.
Yeah, you can close the other server once it is open.
Hmm.
So all the students, please ensure that whenever you are logging off out of your session, only then the entire work will be synced to the all the servers. Okay.
Okay. So this is the same structure. I'll just hide the mesh for you to for it to be more clear. There
Yes.
is just one small change. I had made the channel length to be 12 nanometers instead of 15 nanometers.
No problem, no problem. That is something which all the students have to change anyways. So
Yeah.
that is something is the part of your RP.
And already we were just what we were doing was that we were trying to copy the CMD file, the test file, since it is already copied here. So
So you can
this
just
is our
open
test
up
file.
one. You can
Yeah.
open one, and you can explain the part where they need to get involved.
Yes.
Okay.
So once the test file is already there in your folder.
No, no, no. Open that text file, please, in the gedit.
Okay. Okay.
I want them to see what is there. Like, why are we even including this text file? Yeah. So all of you please note that this text file is essentially the stimulus file essentially. Okay. So remember, whatever you have done in the SDE is the device, the mesh, the doping and everything, right? So now whenever you want to run the simulations, you have to also specify the voltage goals. So like what is the voltage variation which you want to record, because you are essentially looking for some IV and CV measurements or CV curves, right? So CV simulations, IV simulations, तो आपको बताना पड़ेगा ना कि how much is the voltage changing, VGS, VDS कितना value होगा वगैरह. All these details are given in the CMD file, as you can see. This is the command file, short form CMD. So here in the first step, you will find there is a file section, as you can see. The file section at the first part of this top file, top, you can see this here. Over there, you'll have to specify the and mention the path of the TDR and all that. Okay, I think Aditi, you have not showed how to save the structure.
Sir, I saved the structure.
Save the structure, no? So
Yes, sir.
whenever Aditi has saved it, automatically Centaurus will save it in all these file structures. Okay, TDR, then parameter files and everything. Okay.
Like these are the different files.
Exactly, exactly. They will automatically get
TDR.
saved, so you don't have to worry about what of these. So, what are the significance of all of them? We will learn after you have learned the tools, after the end sem is over. Okay, in the summer break, I'll give you all the details. Okay, can you open up the text file once again?
Yes, just one small thing.
Yeah,
Once the students simulate it, they will get a message that the parameter file is not there. So they will have to include the silicon germanium.par parameter file.
yeah,
Okay.
exactly. Acha, why is that? Because students, you should remember that if it is pure silicon, we do not have to bother about the mole fraction and stuff. But since we are using silicon germanium, why are we using? We have again discussed this in details in the physics and modeling of microelectronic devices PMMD course. Silicon germanium is a strained silicon. So that means with the strain, the mobility increases. So it is a very well known and established fact that if you can introduce strain in the silicon material, the mobility improves and hence the mu n C of W by L VGS minus VT whole square, mu n increases. So the current increases. Simple. Okay. So here what we are saying is that the parameter file, as Aditi is showing, in the file section you are showing the path of the parameter file also. Uh, can you open the parameter file? Yeah, it's
Yes.
correct. So in the parameter file, if you will notice that it will have all the details of the silicon germanium and also the mole fractions you are going to change as required. Okay. The physics of this, if you're interested, we can again, I will discuss this later on. Okay. How does all these values, if you see, they are essentially giving the values for 0 and 1 for each and every parameter. If you see 0 1 0 1 0 1, what is that? Remember, silicon germanium is Si1 minus x GEX. That means this x value is this bracket में जो 0 and 1 है वो. So that means if you are putting x equal to 1, that means Si mole fraction is 0, Ge is 100%. Okay. So Si 1 minus x Gx. So that means if you are putting x equal to 1, sorry, if it is x equal to 1, it is germanium. If it is x equal to 0, it is pure silicon. Okay. So that means all the parameters like mobility, here for example, like let us say electron affinity, all these parameters, epsilon value, these are all essentially functions of the mole fraction of how much mole fraction of silicon is there, how much mole fraction of germanium is there. Okay. So all these 0 and 1 values are essentially set for pure silicon and pure germanium. Correct? So what Centaurus will do is, based on the mole fraction which you are entering into in your CMD file. Can you open the CMD file once?
Yes.
Yeah. So in the CMD file, what mole fraction you are entering over there, based on it, it is going to find out the uh, exact value. Here, if you see in the physics, Aditi has mentioned the X mole fraction is 0.65. So what does it mean? It is silicon is 0.35 and germanium mole fraction is 0.65, as she has mentioned in the comment also. GEX SI1 minus X. Got it, everybody? Huh? So this is what she is putting in. So one part of your RP will be how the device characteristics will change if you are changing the value of the mole fraction. So as you go more and more, as you doping, it's not doping, however, if you are putting the higher and higher mole fraction of germanium in silicon, that means you are essentially increasing the strain. How that means X is increasing, how much variation in the current will happen. Got it, everybody? So that is also part of it. Here she has taken one arbitrary value 0.65. Okay, yeah. So all these details have to be mentioned in the command file, which will be used during the Centaurus simulations. Okay. Now later on, these are the physics section. What are the various models to be used? Can you scroll down? Oh, excellent. So notice these are the mobility, effective intrinsic density, recombination, SRH, that is Shockley Reed Hall recombination parameter, Auger. Then band to band is the tunneling generation for the tunnel fed. So in all the simulations, if we are doing for MOSFETs, for instance, we need not bother about this band to band line. Whatever this is, actually whatever we are writing, the script which we are writing in the CMD file is in the TCL. Okay, the TCL, that is tickle scripting. So in the tickle scripting, what we have mentioned over here, each of these commands, band to band, auger, these are the reserved words. These reserved words are essentially referring to the various class files which are being called in during at the time of the simulations. Okay, as I told you, if you are a developer in Synopsys, what you have to do is you have to develop each of these class files. That is what I had to do when I was uh, in the R&D of Synopsys. So that is the job description. So now, as a user of Synopsys, you have to simply call the class file. So if you are calling in the band to band over here with the model is non-local path, what happens is it is going to call the model. Remember, the course name was Physics and Modeling of Microelectronic Devices. So that means all the models which we had studied in our PMMD course is only like 10% of the models which are being used in the modern technology today. Okay, so Synopsys has got the entire repertoire of all the models available, and they are always increasing the number of models fed into the actual data, actual code. What happens is that this will essentially improve the use cases of Synopsys or Cadence in that fashion. Okay, so you can put in more and more new devices. And for example, we are working on memristors. So this memristors do not have a model. So in the future, when somebody comes up with a model, that model will be incorporated as one of these header files which you are seeing over here. So somebody 20-30 years ago came up with this band to band application model which is incorporated in Synopsys. Remember, not the mathematical model. The mathematical model was developed by Kane in 1960s in the with the tunnel diodes. Don't confuse with that. How Synopsys incorporates those mathematical models is the question over here. That is being coded in C++ and put in over here. So that is what Aditi is using right now. Okay, the band to band. So all these are given. For example, temperature is mentioned. So I can ask you, what is the temperature variation? Variation of the IV characteristics with temperatures. All you have to do is you have to change this value 300, temperature equal to 300, with let us say steps of 50 degrees Celsius or 50 Kelvin. These are in Kelvin, by the way. Okay, so that is what you have to do. Then that is the physics part, which models, physical models you are selecting. Then lower down below you will find the math part. Math part essentially includes what are the various numerical methods which we are going to use over here. For example, we are giving the data like you have to do the extrapolate. Then what are the significant digits to consider? That is number 5. Error reference for the electron and hole are also given. So that means the numerical methods will go on trying to simulate until and unless the error reference reaches 10 power 15. After it reaches 10 power 15, so you can see this is error. So अगर error ही 10 power 15 हो जाए, that means the structure does not converge. So that means the structure will not work in practice. Got it? That means that structure, the device is not going to work. Okay, so that is what we have done. So for example, she has commented out the number of iterations because either you put the error reference, that means if the error reference goes beyond 10 power 15, stop the simulations. Okay, or else she has commented out this one, iterations is 100. So irrespective of the error, it will simply go on doing the iterations for 100 cycles, and after 100 cycles, if it does not converge by that, converging means the error should be going to 0, as close to 0 as possible. Okay, how much close to 0, that will be given in the solve section. Can you please scroll to the solve
Yes.
section once? Yeah.
Yes.
So I'm just giving you a cursory glance about what this CMD file is doing. In the solve section, if you notice, the first one is the initial. So that is something everybody knows. If you want to do any numerical methods, first thing is that you have to start with the initial guess. So that is the initial which we are trying to do. Then the iterations, as you can see, iterations have been given as 100 for, but this 100 is not similar to the iterations which we mentioned in the math section, because this iteration is referring to the initial condition के लिए simulation. Okay, so here we are doing the coupled Poisson electron hole simulations, Poisson simulations, and all that. And after that, we are going to the quasi-stationary simulations. So that means quasi-stationary means essentially DC values. Okay, remember these IV characteristics are DC characteristics. AC के लिए हम बाद में देखेंगे. When we are essentially looking for the CV measurements, okay, or CV characterization. मतलब voltage के साथ voltage के साथ आपका CGS और CGD कैसे change हो रहा है. Okay, that will essentially come only with your AC simulations. Here we are doing the DC. All right, so in the quasi stationary, if you see, the initial steps are given. Matlab steps means these steps are essentially telling you the step size for the numerical simulation. So it will start with 0.5, increment 1.3, but 0.5 1.3 is essentially the factor by which the initial steps will change. Okay, so that means after initial step, probably it will go with 0.5 of the initial value, then it will go on incrementing 1.3. When it does not converge, it will decrement by 1.5 and it will essentially go on. So what is the minimum step? What is the minimum step over here? It is 10 power minus 10. What is the meaning of that? So the simulation will continue as long as either the upper limit is here 10 power 15 in the math section, or the lower limit here in the solve section is 10 power minus 10. That means when the error has gone to 10 to the power of minus 10, we will say that it has converged. Because if it is numerical methods, why 10 power minus 10? If you need more accuracy, you can even mention 10 power minus 20 also. So that means unless and until the error goes to minus 10 power, unless and until it goes to 10 power minus 20, it will assume that the simulation is still going on. So you have to ensure that how close to zero you are essentially coming to. Okay, na? So that is the minimum step size is 10 power minus 10, where you are telling the Centaurus to stop the simulations, and then we will say that it has converged. So that means it has reached a solution. These are basically the simple terms of numerical methods which probably all of us are a little bit aware of. Then whatever results we are getting, it will be saved in the prefix id underscore ntfet dot plt, which Aditi will show now. Okay, then this is
Yes.
coupled Poisson electron hole, and these are essentially the now again another thing, if you'll notice, we are mentioning something like a goal. Okay, notice this is what is the goal here, G, and voltage is 1.5. Now if you go to the top of the here, if you notice that in the electrode the initial voltages were essentially provided as these values. See, the drain is provided as 1 volt, source is provided as 0, source is grounded, the gate is also grounded, and towards the end of this file, uh, at the solve section, where we are telling that the goal is 1.5. So what it means is the VD will be kept, the drain potential will be kept fixed at 1 volt, source potential will be kept at 0 volt, whereas the gate will be swept between 0 to 1.5. ओके, तो हम यहाँ पर क्या कर रहे हैं, आईडी वीजीएस प्लॉट कर रहे हैं, आईडी वीजीएस. ओके, so I think that's all. That is more than enough for your understanding of the CMD file. So all these details have to be mentioned in the CMD file. So this CMD file will be shared with you. Either Aditi will share or I will share. Doesn't matter. Now what you have to do is you have to tweak these values, whatever inputs you are doing, and we need the results out of the simulation. So what you are trying to do over here is that first case of your RP after the end sem is over will be to find out how the device changes with all these parameters changed. Then once you have been well accustomed with the simulator, then we will go even further. Okay, over to you, Aditi. Thank you so much.
Yes. So now that the test file is here, we will run it once in S device. So this is the solve section going on.
Here, if you will notice that
Sir,
they,
just
yeah,
excuse me. There is a phone coming from office. I'll just take it. I'll just mute my.
yes, you can go
Yeah.
to another room. Yeah.
Yes. Yes.
So, or you can mute yourself. All right. So what I'm suggesting here is that if you will notice these iterations are continuing now. So you will find these are basically Newton-Raphson. Remember that Newton-Raphson or is the very very standard finite element method which is used in all the simulators. So whenever you are using LT-Spice, Cadence, Synopsys, Vivado, all these numerical simulators are essentially using Newton-Raphson only. Okay. So here, if you will notice that we are essentially telling about the step size and it is doing the uh, simulations. Okay. So Newton-Raphson use hota hai. So like those of you, if you are really interested, I mean Newton-Raphson is essentially the fastest one, but the most inaccurate one. Okay, so Newton-Raphson gives you the first-hand experience or first-hand results on how the simulations, I mean, how the device will work and all that, how the circuits will work in the case of cadence. But Newton-Raphson is definitely not the most accurate one. So what is more accurate than one? So there are several techniques of carrying out the numerical methods. One solution is the Newton-Raphson, as I'm telling you what is happening over here. The other better option is called uh, uh, I'm the that is I'm forgetting the name because that we don't use it much. The even better than that one, it's not coming to me. NEGF, yeah, it is called NEGF for non-equilibrium green function. Okay, so we can use the NEGF formulation for doing the same kind of simulation. So same, everything will remain the same, but you have to specify that instead of Newton-Raphson, you have to use NEGF, non-equilibrium green function method. Even more accurate than NEGF is Monte Carlo, MC. Okay, so during my PhD, I had worked on. Look, here it is mentioned. Newton didn't converge. Trying again with the smaller step. Newton didn't converge means Newton-Raphson didn't converge. Okay, so non-equilibrium green function is there. So similarly, when it is not converging means it will take a smaller step size and do carry out the simulations. All right. So once this Newton-Raphson goes on, I mean, you can have the other option is NEGF, non-equilibrium green function, as I said. Even more accurate than that will be, look, another one. Newton didn't converge. Trying with smaller step. This Newton is referring to the Newton-Raphson. Then the more more accurate than NEGF is MC, Monte Carlo. Monte Carlo is the most accurate one among the standard three forms of numerical methods, as I'm telling you. But again, it is the most time taking and but the most accurate. Then in modern state of the art, people are essentially, look, again there is a problem. Newton didn't converge. Trying with this. Okay? So we are now the step size, if you can see, this 0.029. Earlier it started with zero point 0.1. All right. So in the modern, the state of the art is essentially to use data-driven modeling. Okay, that is what I've been emphasizing you time and again every time. Okay, in the course and everywhere when we meet. So in data-driven modeling, what happens is we are essentially going to predict the step size. Here it is doing in the old-fashioned way, just running and trying to. This is hit and try. In the machine learning based or data driven modeling, it is essentially going to trace out the variation based on machine learning. So machine learning is an added tool over the numerical method. So probably within the 10-15 years, you will find all these numerical methods based simulators will either incorporate machine learning tools in it, or else they will be simply replaced by machine learning based simulators. Okay, so if you want to survive for the next 20-30 years of your career, you must learn machine learning some way or the other. I'm telling you. So this is the old-fashioned way of numerical methods. No matter which method you use, finite element method or NEGF, non-equilibrium Green function, or Monte Carlo, they are all kind of going to get obsolete. Yeah, Aditi, you can continue. Yes.
Yes, sir. Actually, this simulation is taking long. Actually, I had changed the voltage to 1.5
Yes.
volts,
Yeah.
after which only this long calculations came. Earlier, when it was at 1 volts, it was very limited.
No, it is almost over. Look, it is
Yeah, yeah, yeah.
0.94. So let us wait for some little more time, then it will be
Yes.
over.
That convergence issue was not there till 1 volt, sir. After 1.5, there was a lot of convergence issue, and hence this calculation is like going on and on.
Okay. No, I asked you to finalize all this before the demo. Anyways, so is it no? Is it
No, I
continuous?
had finalized only. In the demo, I would have taken 1 volt, but because of the server problem, I didn't know that it will not
Okay, no, no.
populate
Is
again.
it coming down? Yeah,
Yeah, yeah, it's
0.98. You see. Or else, what you can do, if you stop this, you are going to have the PLT file until how much? It is done. T equal to
yeah,
1.
yeah, yeah. It's
It's
done.
over.
It's done.
Yes, yes.
Yeah. So for the PLT file, we'll open as visual. So this is the PLT file. This is the name that we give, ID underscore, and then the model name. In this, we'll select the gate voltage to be on x-axis and drain current to left y-axis. So this is our current. Can put grid markers over here for curve markers over here for more clarity. So we can see that near to 1.5 volts of VG, our current is in the orders of 4, 5 microamperes. Hello. Yeah, so we the current is in the order of around 4 to 5 microamperes over here. What you can do is you can keep on changing the material mole fraction mostly. What we can change is we can change oxide also, the gate oxide, front gate oxide that is. We can take a higher dielectric material, or we can reduce the body thickness, the gate oxide thickness and all, to keep on optimizing the current to the maximum. Like our aim should be to get maximum possible current from this gate voltage. What
Maximum
we are
current, maximum possible on current. Huh? That is the on current over here.
on current, yeah,
Yeah.
yeah.
So that means on current कब कहते हैं? Like I have already explained this in the classes, in the courses. Whatever is the VDD or the maximum VG which you have applied. Okay. So here Aditi has used 1.5, but remember, if depending on the technology node, suppose if you are using the channel length of around 45 nanometers, you should not go around 1.5 volts. The electric field will be so high, it can lead to a breakdown. Just to keep things in perspective, notice that uh, in this device, what was the channel length which you have
So
used?
that took 1.2, sorry, 12 nanometers.
12 nanometers. Okay. Notice if it is 12 nanometers, okay, channel length, so that means channel length is pretty small. In that case, if you are going to use, I mean, as you can see in this curve, the more the voltage is increased, it was having problems in the simulations. If you see beyond, let us say 1.2 volts or something, as you see, there are so many data points. Why is it so many data points? Because the device is not able to, converge in the Newton Raphson. That means if it does not converge, means what? The device will not work. That means why will it not work? That means the electric field is so high, there will be breakdown and all happening. Okay. So instead of 1.5, suppose she has applied say 5 volts, the device will never work. It will not converge until the 5 volts. So that means beyond, let us say, this 1.5, it is becoming difficult. That, I mean, simulation, I mean, the calculations are becoming difficult. The reason being, it is going more and more towards
Breakdown.
breakdown. Got it? So these simulators are so helpful. It will give you a clear idea once you get the results. Initially, you might be thinking that, okay, what is the point in doing this simulation? This is simply some software which you're using. No, not at all. Either you do experiments or you do the simulations. In fact, simulations are way better than experiments, because remember, whatever she has done, it is the work of 1 month to actually fabricate one device and get it. Now, what you are going to do, you are simply going to change the oxide thickness. What does it mean? That means you have to fabricate a whole new device with a different oxide thickness, which is not possible so easily. So, if you want to actually learn the device, you should use simulations very well. Simulations then make sense of the data. For example, I am able to say make sense of the data. For example, what Aditi was telling little while ago, that she has changed from 1 volt to 1.5, and that is the reason why it is having so much errors of convergence issues. Why? Because she has increased the VDD, and the device is unable, with 10 nanometer channel length, it is unable to withstand that much amount of electric field. It is going into breakdown. Got it, everyone? Huh? So now you will see that in 1.5 it is giving you a higher volt. So it is quite obvious. Like if you increase the voltage, you are going to get an on current of higher on current. But remember one thing, that really doesn't make any sense, because when you are actually deploying the circuit at, let us say, some particular technology node, then the VDD will be fixed at 1 volt only. है ना? तो यानी कि आपका ऑन करंट क्या होगा? ऑन करंट इज द करंट विच इज एसेंशियली ऑब्टेन्ड बाय द डिवाइस at the when you have applied VDD to VGS. Okay, अब VDD कौन सा फिक्स करोगे? For example, in this device, she has given VDD of 1.5 volts in the VG. That is fine, but as you can see, it is getting some issues with the convergence. Okay, so if from the reliability perspective of the device, you should use a VDD which is lesser. So I have taught you in the advanced VLSI design as well as in the PMMD that VDD is essentially determined based on the reliability of the device. So now the question is, in this device, you can see that it is having some issues. Now it is 10 nanometers. Or in the technology node, what we have found, that in 45 nanometer itself, we are using 1 volt as the VDD. In 45 nanometers, यानी कि channel length 45 nanometers है, वही हम 1 volt use कर रहे हैं. ठीक है ना? यहाँ पर देखो, ये 10 नैनोमीटर टेक्नोलॉजी है. ये channel length 1.2 nanometers she has taken, right? So in 1.2 nanometers she has applied 1.5 volts. So obviously there will be convergence issues. So it has worked for this particular thing, that it is like you are lucky, but it is not lucky enough, because you know what, if you change the VG little bit here and there, if you modify the thickness little bit here and there, it is not going to converge. Now the point is, why is that an important part of understanding? Because remember, when you are changing little bit of oxide thickness, why? Remember, the oxide thickness she has used is how much, Aditi? 3 nanometers, right?
Yes, sir.
3 nanometers. So how can you always ensure that your oxide thickness will be exactly 3 nanometers? You can't ensure that every transistor will always have 3 nanometer oxide thickness. It will be 3.1, 3.2, it can be 5 nanometers also. The moment it is 5 nanometers or less than 3 nanometers, your simulations will not work. Got it? Simulations will not work, doesn't matter, but imagine the real case when you are actually doing the fabrication in AMD or Intel or Global Foundries. In those cases, every device batch processing lost means millions of dollars gone to the drain. You can't afford that. Okay, so always always keep the reliability of the device in mind. That's a very important thing. So if I get a paper in which people have Aditi has written one paper and it has come to me. The moment I see so many of simulation, convergence issues over here, the first thing that it will creep into my mind is that the device is going more and more into the breakdown. Okay, so the first thing that so remember, synopsys TCAD is basically a device tool. इसमें circuits नहीं है. तो circuits में तो आपका यहाँ पर with some particular voltage situation, particular set of stimulus in the circuit, it can happen that the voltage will be higher than 1 volt or VDD. Immediately the MOSFET will be burnt off. MOSFET, FinFET or tunnel FET, whatever, the device will be burnt off. Okay, so you have to keep those things in mind. All right, so the on current is essentially the current ID for when you have applied VDD to the VGS. Okay, now what is the off current? Aditi, can you click on the log Y? Excellent. So what you have seen in the linear scale is essentially uh, the on current. In the off current, you can see, as I have told you in the class, remember, in the linear scale, you will not see any current below the threshold voltage, right? Now, the below threshold voltage, you can see the off current is when you have applied 0 volt to your VG. ठीक है ना? तो VG अब जब 0 है, तब देखो करंट आपका 10 पावर -9 से भी काफी नीचे है, in the order of 10 power -10. Okay, it is lower than 1 nano ampere. Now the question is this a very good device? Remember, that means if you are switching on the device from 0 to, let us say, you are switching on, right? So that means आप 0 से अगर VT तक change करोगे, let us say the VT is around 0.5 or so. Notice the slope is very, very slanting. Okay, the slope is very, very slanting in the sense that means the slope is not that sharp. That means the inverse subthreshold slope is very high. We are supposed to get it as low as
possible.
Okay. Now, can you just show the screenshot of the device which I showed you, Godfrey?
Yes, yes.
अभी Godfrey दिखाने की जरूरत है, सिर्फ वो ग्राफ दिखाओ, so that they can compare. ठीक है? This is the standard TFET. So your research should begin with the standard, as Aditi has rightly done. पहले आप standard TFET स्टडी करो. Godfrey जो हमारे ग्रुप का, I mean, we found that out. It's our own discovery. मैंने जो आपको दिया था,
हाँ sir, that's on 741 actually. वही मेरे साथ that problem is occurring. I didn't know what was the cause of it.
No
It's on this one.
So you have seen the slope over there, students, right? So now we will show the device on the basis of which we have essentially published so many papers. Our students have graduated. So this is the case of the Godfrey. इसका log वाला नहीं है क्या?
Just a minute.
log नहीं है.
Log नहीं है sir.
यहाँ पर एक PLT फाइल खोल के देखा सकते हैं?
Yes.
Then this will become very, very clear to them. What is a good device? What is a bad device? Okay? So what is our target in your RP? So Aditi will be working on FinTFETs. FinFET जैसा है, उसी तरह का FinGodFET जैसा हमें करना.
So is this the one? This.
हाँ, you can show that also. So it should be the same. How to show this will also be, I mean, Aditi will show that. Yeah, can you go to the log one? Yes. So now if you compare with the previous one, as you can see, the slope is much, much sharper. And notice the on current is crossing how much? 0.001 amperes.
1 milliampere.
That means what? 0.001 amperes means 1 milliampere. अब एक बार log y को click करो, on current दिख जाएगा. Aditi, click on log
sorry
y.
sir?
Click on log y once again.
Okay.
I am just trying to show. See,
Okay.
in the on current, that means 1 volt में आपका ये 1 milliampere cross कर रहा है. Students, are you observing? So that means it is actually performing as good as a FinFET. FinFETs, the FinFET which is running on your smartphones, they have the on current of around close to 800 or 900 microamperes. So that means this Godfrey is theoretically, remember यहाँ पर ये कोई fabrication हमने नहीं किया. Theoretically, the Godfrey is able to perform better than a FinFET, which is the current standard technology. ठीक है ना? एंड देन अब ऑफ करंट का देखते हैं, लॉग वाई क्लिक करो प्लीज। एक्सेलेंट। अब ऑन करंट देख लिया 1 मिली एम्प से ऊपर है, एंड द ऑफ करंट देखो ये पिको एम्पियर से भी नीचे है, विच इज बेसिकली नॉट नेसेसरी। व्हाई? बिकॉज आपका नॉइज इटसेल्फ विल बी इन द ऑर्डर ऑफ 10 पावर माइनस 10 नॉइज। ओके, तो यानी कि अगर इट शोज वेरी नाइस, इट लुक्स वेरी नाइस ऑन पेन एंड पेपर, okay, I can claim that okay, the off current is 10 power minus 12, but it is basically nonsense, because in practical reality what will happen is your noise current itself will be around 10 power minus 10. तो यहाँ पर आपका जो basic I mean the static leakages, whatever we are saying, no, the static leakages will be governed by the noise itself. Okay, however there will be no leakage because of the device, but the thing is the static leakage ये 10 power minus 12 है, यानी कि अगर आपका the whatever noise you will be getting in the circuit will be because of the ambient noise itself, thermal noise, flicker noise, okay, all those. All right, and look at the subthreshold slope. Subthreshold slope is very, very sharp in comparison to the standard tunnel FET which Aditi is showing you right now. Okay, that's all, Aditi. So now you can go back to your original simulation. Okay, so what students, what you have to do is essentially you have to use the standard TFET, little bit work on that, try to improve on it, and then what we will do is we will share with you the GOTFET device, and then we will ask you to improve upon it. So now you can clearly see the subthreshold slope difference. Okay, more about the TFET theory we will discuss after the end sem is over. I'll call you during the summer break. But as of now, you should be aware of the simulation tool because we'll be using it for your art. Okay, over to you, Aditi. Thank you so much. Yeah.
Yes, sir. So this was the NT-FET demo, as sir explained various aspects of it. And
Another thing is that Aditi, please show them
yes,
how to get the exact value of the current. So that is also very important. You know, right?
like with probe, sir.
Yeah, with probe, yes, with the probe. Because remember, whenever, I mean, you cannot always use eye estimation over here. So the probe will essentially tell you at which point, which one. So for example, in this case, if she is going to write the value. Aditi, go on. Okay.
So like as we move the cursor wherever we click, so this left side, this probe, this thing will appear. Like it will give the exact value corresponding to say this point now over here. So exact value of our VG is here 0.917, and the current value corresponding to that is 3.8 0.38 microampere basically. Similarly, at whatever point we want to see, it can give us to the 5 degrees, to the 5 digits, as we had given in the math section of the .cmd file. To 5 digits, it will give the value,
So now
five
the
decimal
question,
points.
now let, one quick question to all of you. So which device is better in terms of the on current performance wise? Notice Aditi in this device she has done for 1.5 volts. Okay, na? In our previous device it was for 1 volt VDD. तो यहाँ पर
Yes, sir.
अगर 1 volt है, then let us try to find out what is the current seen at 1 volt. कर्सर
Huh.
पे नहीं, हम लोग directly लिखेंगे यहाँ पर. Aditi, you can
So,
directly write over here. I think.
okay.
Just directly write
So,
here. Yeah.
yes, sir.
Yes. Double click.
Actually, sir, it was coming like zero point 0.1 microampere. I just wanted to see how much it goes till. I was just experimenting with different things.
हाँ,
So
no, no,
the
no, 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 it's okay. मैं दिखा रहा हूँ यहाँ पर. Just keep 1.0.
uh, so it's not taking the value. I'm trying, but it's
Okay,
not
okay.
taking the value.
I don't know.
Not taking the value, sir.
So what happens is in that case you just keep it over here. How much is it? Bring the cursor close to one. Click on that. So
Yeah,
if you click on that, you see how much is the value of the current?
it's zero point 0.6 microamperes.
0.6 microamperes.
Hmm.
और हमारे वो गॉडफेट में कितना आया था? More than 1 milliampere.
Hmm.
Okay, so now like our research with Aditi is going to design FinFET kind of structure for the tunnel GOTFETs. So you can understand what 1 milliamps will also go up to like 4 milliamps or something. So that is what our research is. We have to improve the performance. Okay, The off current will be much lower. अच्छा यहाँ पर off current देखो एक बार यदि थी exact value कर्सर को 0 पे लेके आ जाइए. हाँ नहीं
It's slightly, yeah.
yes yes इसलिए नहीं दिखाया. हाँ
Yeah.
देखो. Okay, can you see this every students see this 5.648 10 power minus 10 amperes. ठीक है. और clearly in the GOTFET it was much lower than that. Okay, so your task, we will discuss this after your end-sem, will be essentially to figure out the optimal device structure which will give us the higher on current, lower off current, and as sharp the subthreshold slope as possible. That means as low inverse subthreshold slope as possible. Got it, everybody? Huh? So another one thing which you should learn is basically, you know how to export the data to CSV file, Aditi?
Yes, sir.
Yeah, please show them. So let me just finish this. So basically what I'm suggesting is that, remember, here it is just a device simulation. अब इस device simulation करके क्या होगा? आपने तो एक particular, so we want the data out of it so that we can use it for machine learning or we will use it directly for cadence circuit design. ठीक है ना? इस डिवाइस को नया डिवाइस बना के अब जब मुझे cadence पे करना है, then we need the simulation data. That simulation data, how to extract from this simulation is what Aditi is going to show you. उसी में आ जाएगा ना PLT फाइल में. इसी में
Yeah, I just saved it actually.
No, यहाँ पर दिखाओ, just show डेटा में आएगा ना.
हाँ, I just exported it,
Yes.
named
So
it also.
whatever curves, so यहाँ पर सिर्फ एक ही कर्व है इसलिए आपने एक कर्व दिया, तो you just simply save it. Yes, and now open that one. So this is the IV curve simulation which we are going to use for our further design. So in the industry also, what you will find is that this is something which is automated. यहाँ पर ये जो data generate करना, यहाँ से नहीं होगा ना, ये तो plot file है. आपको ये तो
Yes, sir, that's what I was doing earlier. Yeah.
no, यहाँ से अलग से open करना.
Yeah. मैं वही कर रही थी सर, आपने बोला तो मैं फिर से उसको सेव करके देना इवेंट पे.
हाँ, okay, so start recovery करो.
Yeah.
Okay, finish. Yes, excellent. Okay, fine. So you see, these are the data points. Now, if you take more number of data points, you will have more amount of data, which will be useful for the ML. But as far as your cadence is concerned, you really do not have to bother so much about this number of data, because cadence will essentially use interpolation. Okay, yes, if IV curves हो गए, then if you want the data about the electric field and stuff, that is also possible using S visual. Okay, so okay, over to you, Aditi. I think it is done.
Yes, sir, it's done, sir.
Okay, so I'm going to stop the recording now. So you have got the brief overview of how to do the simulations, and after the NSEM is over, I'm going to call the RP students, and we will have a meeting with Aditi, myself, and all the students, and essentially we will give you the device and the CMD file. What you have to give us is that individually each one of you are going to take care of one parameter of the device. One of you will vary the oxide thickness. One of you will vary the source channel length, structure, dimension. So one of you will vary the doping level. So ऐसे करके आपको क्या करना है? You have to give me the data. ठीक है? वो PLT फाइल करके मुझे CSV फाइल देना है. So with this data, we are going to get an optimal solution using machine learning, which will essentially give us the best possible device which you can get. The GOTFET was essentially done like that only, but this will be a training with the very, very ordinary conventional tunnel FET. So once you have got your hands-on experience with it, then we will give you the current state of the art in the tunnel FET. That is the GOTFET. Then उस GOTFET के बाद हम लोग क्या करेंगे? उस डिवाइस को हम cadence में लगाएंगे. ठीक है? So in cadence, how to do it is Verilog AMS. We will see as we go along in the research work. Okay, this is the first demo. So thanks to all of you for joining. I'll close the session now. We will also have the further discussions on the physics behind tunnel FETs in details after you have started working on the GOT-FET, after you have started working on the TCAD simulation. So once you are able to generate the data on your own, then you will essentially face a lot of problems. Aditi is expert now on using the tools, so you can refer to her for the tools and all. So any discussions regarding the device physics, device circuits implementation and all that, you are always free to come to me. Okay, thank you for joining. Thanks a lot. I'll close the session.
Thank you, sir.
Thank you, Aditi. Thanks a lot.